Welcome to our presentation on gravity, clustering and dark matter in the context of astrophysics and cosmology for PHY 4605. In this project, we will explore the gravitational forces that shape galaxies and large-scale cosmic structure. Our team includes Najwa Shuhada, Umi Umaira and Fatih Nurin Nabila, and we will dividing into how gravity and clustering work, particularly in relation to dark matter. Gravity shapes galaxy and large-scale structure in the universe. It's always attractive, which means it dominates over time. However, visible matter alone can't explain galaxy motions. This is where dark matter comes in, an unseen mass that affects gravity but can't be detected directly. Using MATLAB simulation, we can visualize how dark matter influences the gravitational clustering of galaxies, helping us better understand its role in the universe. According to Newton's law of gravitation, every mass attracts every other mass. The force between them depends on the product of their masses and the distance between them. The closer the masses, the stronger the force. In the early universe, everything was almost uniform, with small regions being slightly denser than others. This led to what we call density fluctuation. Gravity pulls matter toward denser regions, causing them to grow even denser over time. This leads to the formation of clusters of matter instead of the uniform universe. In low temperature system, particles have very small initial velocities and gravity becomes the dominant force that controls their motion. The clustering time depends on mass density. The higher the density of the mass, the stronger the gravitational attraction. This leads to faster clustering. Stronger gravity causes denser regions to form structures more quickly, speeding up the process of clustering. This simulation models a 2D system of particles interacting through gravity. The particles are randomly placed inside a square region and start with a small initial velocities, representing a low temperature system. Simulation steps: the user selects the number of particles. The gravitational force on each particle is calculated from all other particles. The particle motion is updated using Newton's second law. Observation: in low density area, particles stay spread out. In high density areas, stronger attraction leads to gravitational clustering.
So, this code is to simulate the motion of particles interacting through gravity. Firstly, the user will input the number of particles. Next, the gravitational constant, the time step, and total number of steps are defined to control the simulation. And then we initialize the particle position, velocity, and mass. So the position is initialized with a random position and with a small random velocity. And every particle will have the same mass, which is 1. And next we are plotting the figure. The figure is to show and animate how the particle move and form a cluster. And then this simulation, it runs in a time loop, which at each step, gravitational force between every pair of particles is calculated using Newton's law of gravitation. This one. And then, after that, the velocities and position of the particle are updated, which is based on the total force that is acting on them. And then finally, the updated position is updated on the plot, which later will form a animation-like simulation. So, this is example of clustering that happened. And now we are going to run the simulation to see how this code runs. So we enter a small number of particles first. And you can see the particles still move towards each other, but it happened very slowly. And now we are going to run again and enter a higher number of particles, such as 300. And as you can see, the particles move towards each other very fast and form a cluster. And
this graph shows the behavior of particles in the system based on their density. When the number of particles is small, the particle remains scattered and don't form clusters. When the number of particles is large, the particles move closer together and form clusters. This happens because the gravitational force increases as more particles interact with each other, causing them to group together. Gravitational clustering helps explain how matter forms structures in the universe. However, visible matter alone can't explain all of our observations. For example, galaxy rotation curve shows that the stars are moving faster than expected. This suggests that there is more mass present than we can see, which leads to the concept of dark matter, an unseen form of mass that we know exists because of its gravitational effects. Most of the universe is not made up of visible matter. Visible matter includes things that we can see, like stars, planets, and gas. However, dark matter cannot be seen directly using light. It interacts mainly through gravity and makes up a large portion of universe mass. Dark matter plays an important role in galaxy formation and motion, even though we can't see it. Stars orbit the center of a galaxy due to gravity. Normally, we expect orbital velocity to decrease as we move farther from the center. However, outer stars move faster than predicted by visible matter alone. The observed velocity remains nearly constant at a large radii, which suggests the presence of additional unseen mass. This behavior indicates that visible mass cannot explain the motion of stars in galaxies, pointing to the existence of dark matter. Massive objects can bend light from distant sources, a phenomenon known as gravitational lensing. This effect happens because light bending depends on the total mass of the object. Strong gravitational lensing can even form Einstein's rings, which are circular arcs of light. The observed lensing is stronger than expected from visible matter alone, indicating the presence of unseen mass, likely dark matter. This simulation models the rotation of stars in a galaxy. Stars orbit the galaxy center due to gravity, and the galaxy mass is divided into visible matter and dark matter. Simulation step: define the distance of stars in the galaxy center, calculate the rotation velocity using visible matter only, add a dark matter halo contribution, recalculate the rotation velocity including dark matter, compare both rotation curves. Observation: with visible matter only, velocity decreases with distance. Include dark matter, velocity remains nearly constant. Dark matter explains the observed flat rotation curves in galaxies.
First, I define G, the gravitational constant, with value 6.674 times 10 to the power of negative 11, with units of meter cube per kilogram per second squared. Next, I define M sun, which represents the mass of the sun. Its value is 1.989 times 10 to the power of 30 kilograms. And then here I represent the distance from the center of the galaxy. It ranges from 0.1 to 50 kpc using 500 points to produce a smooth curve. I then convert the radius from kpc to meters, which is required to keep the calculation in SI units. Then I define the mass of visible matter in the galaxy. I assume the total visible mass of 10 to the power of 11 solar mass. And I then define the dark matter halo mass. In this model, the dark matter mass is 5 times larger than the visible mass, which is consistent with observation of spiral galaxies. Here I calculate the rotation velocity due to visible matter only. So this equation comes from balancing gravitational force with centripetal force. The velocity is proportional to the square root of gravitational constant times mass divided by radius. Next, I calculate the total rotation velocity including the dark matter. The dark matter mass is assumed to increase with radius, representing an extended dark matter halo surrounding the galaxy. I then convert the visible matter velocity from meter per second to kilometers per second. I do the same conversion for the total velocity including dark matter. Now plotting, I create a new figure window with a white background. Here I plot the rotation curve due to visible matter only. So these represent the expected velocity without dark matter. I then plot the rotation curve including dark matter, shown as a solid blue line. I label the horizontal axis as the radius from the galaxy center in kpc, and for y, I label the vertical axis as the rotation velocity in kilometers per second. Then I add a title: Galaxy Rotation Curve Visible versus Dark Matter. I also included legend to distinguish between two rotation curves. And finally, I add a grid to improve the readability of the graph. So if I run this code, here is the result of the code. So the red line is the visible matter only, while this blue line including dark matter.
This graph compares the rotation velocity of stars near the galaxy center with and without including dark matter. The rotation velocity is high near the galaxy center for both cases. With visible matter only, the velocity decreases as the radius increases. With dark matter included, the velocity remains nearly constant. Outer stars move faster than predicted by visible matter alone. The flat rotation curve indicates the presence of dark matter, explaining the unexpected velocity behavior. This presentation highlighted the importance of gravity in shaping galaxies and large-scale structure. While visible matter plays a role, dark matter is essential to explain observations like galaxy rotation curves and gravitational clustering. Through simulations, we showed how dark matter influences star motion and galaxy formation, even though it remains invisible. Ultimately, dark matter is a key component in understanding the universe.